So I guess now we are live. So thank you very much for joining this PQC seminar. The videos and the slides of all the previous talk are now online. So you can access them on the PQC seminar website. So today we are glad to receive Jintai Ding from the Tsinghua University of China and the Beijing Institute of Mathematical Science and Applications. And he will give a talk on UOV, so unbalanced oil and vinegar, signature scheme revisited. So Jintai, you can go ahead.
Okay, thank you, Max. Okay, first I would like to thank NIST for the opportunity to speak here. And this talk is actually part of the work we are working on now. So NIST has one more call for post-quantum signatures, and we have a group of people, and I'm one of them, and preparing to submit to UOV. So this lecture is mostly based on the work we have done on this. And most of it actually I know work before, but I will present a few things new, and maybe I can get some feedbacks from the audience or from people from NIST on the questions we have. Okay, so I'll start now. And today, basically, I'll talk about oil vinegar, and in particular, I'll talk about unbalanced oil vinegar signature schemes. As we all know, and the topic should be categorized in the family of post-quantum crypto systems. So there are 5 main family of post-quantum crypto systems. They are code-based public key cryptography using error correcting codes. They are hash-based public key cryptography for signatures. This is a hash tree construction. And there's isogeny-based public key cryptography using isogeny of elliptic curve. And there's lattice-based public key cryptography using lattice. And the hard problem is the shortest or nearest vector problem. So today, my talk is about multivariate public key cryptography. So I would like to first briefly introduce what it's about, and then I will go into details about oil vinegar scheme. Okay, of course, the context of this work, let me repeat, is because NIST making new post-quantum crypto standards. The first deadline was November 2017, and this already selects 3 algorithms, 1 key exchange, Kuiper, and the 3 signatures, Dilithium, Falcon, and Phoenix Plus. Nevertheless, this decided to have one more round of a signature submission. And let me repeat, so this talk about the UOV, mostly I will talk about the submission we'll do to be submitted to this round of competition. And let me introduce what is multivariate signature schemes. So in the case of a multivariate signature scheme, the public key, which is px1 to xn, is given by a set of m polynomials, which means p1 x1 to xn and pm x1 to xm. Here, each pi are multivariate polynomials over finite fields. And so the private key is kind of different from the traditional ISA type systems. It depends on construction. So in a short way to say it, the private key is a way to compute p-inverse. Okay, signing a hash of documents, basically you can, for example, which is given by y1 to ym, you basically compute a p-inverse and give you a pre-image. So here we do not require p to be a really invertible function, rather than we require to have a pre-image. And verifying is very simple, given pairs, which is y1 and ym. And this is a hash of a document, and x1 to xn, which is signature. You just plug in this pair into the equation, check whether or not y1 to ym equal to p x1 to xn, which means you evaluate x1 to xn using the public key polynomial, and then to see if it's equal to y1 to ym. If it's equal, you accept. If not, you reject. So that's the basic idea of multivariate signature schemes. Okay, so from the construction perspective, we know the public key p x1 to xn should be a surjective map because we would like to sign every document. So this requires, suppose you go from the field of same size to the same, then n should be larger or equal to m. Of course, from practical purpose, we want the signing and the verification process should be very efficient. Also, we want the key size not too large. So this is from practical perspective. And let's look at the security foundation of the system. So given public key, right? So sorry, here I use index G. A direct attack is basically solving a system of multivariate polynomial system, which is G. Here I should type P actually. Px1 to xn equal to y1 prime to y m prime. And in general, we know solve a set of a random n as random system, linear system is with n variables is NP hard problem. Of course, this does not necessarily guarantee the security of the system. So that's the basic idea, which means it's difficult to solve a set of random multivariate polynomial systems, nonlinear. Okay, so here I would like to make a quick review about solving system equations. And this is actually very interesting from the historical perspective. As humans, we were able to solve single variable quadratic equation system during the Babylonian period. So this is around 1800 to 600 BC. And this is what we know how to do already. So this is single variable degree 2 equations. Then it took a long time, around 1500, we start to learn how to solve cubic and quartic equations. Here we should mention two names, Tartaglia and Cardano. Okay, those guys basically found a way to solve those systems. Then we got stuck because Galois came in and he proved that for polynomial system with single variable of degree 5 and higher, we cannot have a closed formula. Okay, and for continuous system, it's actually easy for single variables. You can do Newton methods, which means you can do approximation. But for multivariate systems, we didn't have any really good idea until 1960s. We have a Buckelberg who invented what is called global basis. Of course, in the mathematical world, I think Hironaka knew it already. He called it standard basis. But the key point is that Buckelberg gave a way to compute global basis. And this is a very, very complicated algorithm in the sense of the complexity. Of course, for a single variable, a low degree of a finite field, we have a Butler-Campbell algorithm, we can solve it easily. So if you look at the historical line, actually solving multivariate polynomial system is a very hard problem, which we can see easily. Okay? And so in general, we can also prove that, let me repeat, even a random set of a nonlinear polynomial system with n equations and n variables is NP hard problem over finite. So this is really a hard mathematical problem. And again, let's come back to the perspective from the cryptography, because we want the system to be efficient. So therefore, we actually would like to choose the polynomial of a lower degree. Of course, we cannot choose a linear system. Therefore, we would like to choose the second type, which is a quadratic system. Namely, we will have polynomial system of degree 2, up to 2. On the other hand, from the mathematical perspective, in principle, we can think that the quadratic equation system are the hardest to solve, because given any set of high degree equations, we can do a change of variable in some way to convert it into a quadratic system. A simple example is a system of x1 times x2 times x3 equal to 5. So this single equation can be converted into two equations with more variables. Namely, we can set y equal to x1 times x2. Then we have another equation which is y times x3, and these two systems are equivalent. So therefore, we would like to try our best to use quadratic system to construct multivariate signature schemes. Okay, from mathematical perspective, I mean, we know ISA is based on number 3, and this is a mathematical development in the 18th century. And later, we have the elliptic curve cryptography, and we use theory of elliptic curves, and this is mathematical development in the 19th century. And multivariate public key crypto system. Basically, we're using what is called algebraic geometry, which means based on the theory of polynomial systems. Okay, this is the way to see it. Now, I would like to go down to oil vinegar signature schemes. And this was introduced by Pataran in 1997. Okay, and the development of the system has a long history, which I don't want to go to, but I would like to point out that really the construction of a pathology is very interesting. It is actually inspired by an attack, which is the linearization attack on the Matsumoto Imai crypto systems. Okay, and there were many attempts before to build multivariate systems, but they were all broken. And I think oil vinegar is one of the first that really start to hold up. Okay, now I would like to introduce the oil vinegar signature schemes in details. So we choose a finite field F with Q element. Okay, and let O and V be two integers, and we'll set the number of variables to be n, which is equal to O plus V. Now we'll define the index set. Number one is V, which is from 1 to V, and O is from V plus 1 to N. We denote the variables xi from 1 to V as the vinegar variables, and then the xv plus 1 to xn as the oil variables. So we define those notations. Okay. So in order to create a key pair for the oil vinegar signature schemes, Alice will choose number one, a affine map T, invertible affine map T from Fn to Fn. This is a randomly chosen coefficient. Of course, I would like F to be invertible. Okay, and then second, we'll choose what is called the oil vinegar central map F, and this consists of F1 to Fo, which is O quadratic polynomials, which can also be viewed as a map from Fn to Fo. Of course, clearly here n is equal to O plus V, therefore it is a map from a bigger space to a smaller space. The polynomial F1 to Fo are in the following form. Fi equal to summation jk belong to V, alpha I jk xj times xk, plus summation j from V and k from O, and beta I jk xj xk, and plus linear terms. Okay, and those coefficients alpha, beta, gamma, and the delta, and so on, are randomly uniform chosen from the field F. And if you look at the polynomial system, you can see clearly something is missing. Namely, there are no oil times oil. Okay, and this is the reason we call it oil vinegar schemes. It's like oil and vinegar, they never fully mixed. Okay, and we call this polynomial oil vinegar polynomials. Okay, so we have two maps defined, T and the F. Okay, and then a key pair of the oil vinegar signature scheme can be described as follows. The private key is just the map F and T. The public key, P, is a composition of these two maps, which is F composed by T. And you can see clearly the purpose of T is to protect F, such that we can hide who is oil and who is vinegar. And the end product is a system of n polynomials with n variables. Okay, so here, in contrast to the standard construction of multivariate cryptography, we only use one linear map composed at the right end, because this does not make any sense to put anything into the left end. And since they are random system already, if you add the random system to random system, it's still random system. So therefore, there's no need. So that's the key generation process. Okay. Now let's look at the signature generation. Okay. To generate a signature Z belong to Fn for a random document D, we use a hash function first, hash the document to Fo. Okay, so we compute the hash value W equal to hash of D, and this belongs to Fo. And then we perform the following two steps. First, find the preimage Y belong to Fn of W and the such map F. How do we do that? And this is actually very simple. Here it is very much inspired by the linearization attack, which means what we do is we choose randomly values for the vinegar variables. Okay, just randomly guess the value and substitute them into the polynomial system F1 to Fo. Afterwards, the result system is actually a linear system. Then we can solve the rest of the variables, which is V plus 1 to N, okay, by a Gaussian elimination. Of course, for such a linear system, it's possible we don't have a solution because the system may not be consistent. Then we try again. We guess the value of a vinegar variable one more time. Then we will try to solve the system again, and we will stop until we find one. We know we have a very high probability of a success because this linear system should be a random linear system, and we know the failure probability, which is the corresponding system is not invertible, should be 1 over q. So we should be able to very efficiently get it. Now afterwards, we compute the signature as the T inverse of y, and that's it done. Okay, so these 2 steps find a pre-image of W, which we call the Z. Okay, and let's look at one more time. Why, if we guess the vinegar variables, and then we get a linear system, and use this colored slide, you can see we have oil mixed with vinegar, quadratic terms. The rest are linear terms. Once you set the vinegar to be constant, which I mark red here, and what you get is actually a linear system. So therefore, we can find the pre-image by solving a linear system. So that's it. It's extremely simple. Okay, and then the signature verification I explained earlier is more or less same. To check if Z belongs to Fn is indeed a valid signature, you just take out document, hash it, then plug into the public key. You will compute if W indeed equal to PZ. If they equal, then you accept. If they are not, you reject. That's it. So therefore, the signature verification process is just computing a set of polynomial at a given point and then compare the values. That's it. Okay? And so, of course, as I said earlier, the oil vinegar signature schemes can be viewed as extension of the linearization attack. But you can also look from kind of perturbation perspective. So you can see we can start from a linear system of oil variables, and then we add those quadratic noises through the vinegar variables, and then we try to hide them using the linear transformation T. And when you sign, you're guessing the vinegar variables, which means you eliminate those noise and they go back to linear system. In spirit, this is very like LWE in some sense. Okay, so that's the basic idea. I think this is very simple and everybody can understand fairly easily. Okay, now I would mention a little bit about key size. From the description itself, you can see that computation-wise is pretty efficient because solving a set of linear system is fast, and evaluate polynomials, quadratic polynomial over point is very fast. And then let's look at the key size. The size of a UOV public key is given by O times n plus 1 times O plus 2 over 2. Okay, O is the number of polynomials, and n is the number of the variable. And the size of private key is a very similar formula, which is coming from it's coming from the map T, and the cut it coming from the map F. Okay, and you can see the key size are relatively large if n goes to like 50 or 100. So the public key size and the private key size can be large, but computation is very efficient. Okay, now we would like to talk about the security. Okay, so how secure the system is. When the UOV system come out, and soon after there comes an attack by Kipnis-Shamir. And this is the case on so-called balanced oil vinegar schemes. So here we assume O equal to V. Okay, so that's the attack. So here I would like to describe the attack. And this is still, I consider, one of the main attacks on the UOV schemes. Okay, to simplify our description, we assume the components of UOV are all homogeneous quadratic maps because the linear system doesn't really much. Okay, and then the public key cryptosystem is considered as a set of homogeneous quadratic maps, P equal to F composed by T. Okay, and let's look at the polynomial again. So now we have polynomials which are purely quadratic. Okay, and therefore this polynomial Fx, one of the components of the central map, be viewed as a quadratic form. We can write Fx equal to x transpose. Here x is the vector x1 to xn times f times x. Here we abuse the terminology a little bit. Here we f denote by a matrix f1, f2, f3, and O v times v. The reason the lower right corner is equal to 0 because we have no oil variable mixed with oil variable. So this observation is very important. Okay, so here, of course, from the theory of quadratic forms, we actually we should make F2 and F3 symmetric. So F3 should be equal to F2 transpose if you want to make a unique connection between the matrices and the quadratic systems. Okay, and from this perspective, if you get the public key and the connection between the matrix derived from public key and the private key should be described as P equal to T transpose times F times P. If you use T represent the matrix corresponding to the linear transformation come from T. Okay, so this is clearly how we should see it, and this is the basis of the attack from the accumulation attack. Okay, how do we do that? Okay, to prepare the attack, we need the following definition. Okay, the first we define the Euler subspace of the Fn. Okay, the Euler space are the vectors such that x1 to xv equal to 0, which means the Euler subspace are the vectors with the first v components equal to 0. Okay, and the Vinegar subspace is a set such that the last set of the variable, which means the all variables equal to 0. Okay, so here, of course, we are looking at the case of balanced case, which means n equal to 2v or 2o, I mean n equal to o. And from the perspective of a series of quadratic forms, you observe that actually Euler space is a space such that all those quadratic form vanishes, where namely, if you pick any variables from the Euler space, if you compute the corresponding quadratic form or even the bilinear form, it's always equal to 0. Therefore, invariant description of the Euler subspace is the subspace for all the quadratic form that it vanishes. That's the definition of the Euler space. Okay, so this is the key observation of the attack. Okay. And then from this observation, we can easily see that we have the following properties. If we choose two vectors, u1, u2 equal to O, we have u1 transpose times F times u2 equals 0. This is exactly what I described, which is what? The vectors from Euler space vanishes on all the quadratic forms come from the central map. And because the public key P is coming from composition of F with T, and therefore we know given any two vectors V1, V2 belong to T inverse O, which is the Euler subspace, then we would have V1 transpose P times V2 equal to 0. Okay, which means the transformation T shifted the Euler space to another place. Okay, but nevertheless, such a subspace still exists, which is T inverse O. Okay, so that's the description of the, okay? So the proof is very simple. I mean, I think the computation is very simple. And once you see that, you realize the attack on the balanced or vinegar schemes becomes to find the common to find the subspace of a dimension O such that all the corresponding quadratic forms coming from the public key map vanishes. Okay, that's all. Once you find that, you can find a nice basis and then convert the polynomials back into Euler vinegar form, which gives the equivalent keys, and you can forge the signature. Okay, so that's the basic idea. Okay, done. Then let E be a linear transformation of the form we described. Then we will have following two very interesting properties. Number one is this matrix maps O space to V. And number two, if this matrix is invertible, then we should map what? E inverse V also equal to O because of the invertibility of the E map. And this proof is also very simple. Now, first one, you just compute. You can see easily you map all the Euler space to V. And if it's invertible, since you map, there's no non-trivial null space, then clearly the inverse of of V and the E still is equal to O. So this is the trivial conclusion we can derive it. And with this property, then it gives us insight how to find the invariant subspace. So how to find the null space. So we'll denote by Fi the matrix associated with the ith component of the central map. We'll denote Pi to be the matrix associated with the ith component of the public key. Okay, so here from what we described before, we know Pi equal to T transpose times Fi times T. Then we'll choose two matrices H1, H2 to be random linear combination of matrix Fi. We can assume that the matrix H1 is invertible because this is with high probability the truth statement. Okay, and then the most important corollary is that the Euler subspace O is a common invariant subspace of all matrices in the form of H equal to H1 inverse times H2. And this follows simply from what the lemma we described, which is H2 maps O to V, and the H1 inverse pulls O back to O. So therefore, O subspace is an invariant subspace of this matrix H. Okay, and then from the since this public key P map T are nothing but the linear combinations of those the linear transformation coming from F. Similarly, we can work on the same thing on the public key. Namely, we can do random linear combination of the public key matrices, which will derive W1 and W2, and then we'll compute W1 inverse at W2 and try to find the common invariant subspace, all the matrices. And that's the essential spirit of the Kibini-Shamir attack. Okay, and the statement is very trivial, and you can see that. Okay, so once you find the T inverse O, then as I described, it's very easy. You do a change basis, which means you first find a basis of a T inverse O, and you just add the other vectors and form a basis, and then you do a transformation. Then the new polynomial system will be exactly look like the Euler-Vinegar form, because we know already all the quadratic forms vanish at the subspace, and that's it. Okay, and you would ask me, how do you exactly find the invariant subspace? Actually, this is pretty simple. Actually, I will just give a simple description in terms of characteristics not equal to 2 case, and characteristic 2 case is exactly the same, but for out characteristics is even easier, because first we will write the matrix in the symmetric form. Okay, and then we compute W equal to W1 inverse times W2. Okay, and then how do we find the invariant subspace? Okay, this is very simple, because we can first calculate the characteristic polynomials, and then find all the minimum invariant subspace. And if you do experiment, actually it's very simple. If you do experiment with a high probability, the characteristic polynomial actually coming from product of 2 irreducible polynomials. And given that conclusion, then we can easily using these 2 polynomials to calculate the corresponding minimum invariant subspace very easily, and then we can do it. Okay. And one more thing you would ask: suppose you find the invariant subspace, how do you know it's the correct solution? Again, you check if the quadratic form or the bilinear form vanishes on the subspace. If it vanishes, what do you want? That's it. Okay, so this is a basic idea of the attack. So here, one thing very important is that you have to write down a matrix from the public key in the quadratic form, in the symmetric form. Okay, you cannot just random given coefficients on the corresponding side. No, this is all coming from the symmetric matrices. Okay, and then that's it. You can do what I said, and then you break the system. Okay, so that's the balanced Euler-Vinegar case. Okay, after this was broken, and then Kibini, Pataran, and Gobain proposed soon after, very quickly, a modified scheme called unbalanced Euler-Vinegar signature scheme by choosing V bigger than O. And one question is, can the attack above be applied? Yes. If V is not too far from O, the attack can work essentially in the same way as what I described before. Of course, the space of O and the space V do not have the same dimension longer, and attack works probabilistically. And the description is very simple. Okay. Again, if you look at the corresponding matrices coming from the quadratic form, and it will look essentially the same, except that the lower corner, the zero matrix size is smaller, not the same as the other anymore. So which is O times O. And similarly, we have the following lemma. EO is an O-dimensional proper subspace of O, which means this matrix still will transform the O space into V. Okay? And if E is invertible, then the E inverse V is a V-dimensional subspace of Fn with O as a proper subspace. Okay, and this can be easily checked using matrix computations. Okay. Now you would say, how about performing the same attack, which means I computed the like H1 inverse H2, and then try to find the invariant subspace. And is it possible to work? And then we can prove a very simple theorem says, if W1, W2 can be randomly chosen just as we described, and then we have a probability statement, which is the probability that the matrix W1 inverse W2 has a non-trivial invariant subspace, okay, which is also subspace of T inverse O, is roughly Q O minus V. So therefore, the attack method essentially works, except that the success probability is more or less controlled by Q O minus V. Okay, so and the complexity of the whole process can be estimated by the formula which I described here, QV minus O minus 104. Okay, so that's it. Okay, in my opinion, this is still the most intelligent attack on UV schemes. Okay, so this is it. This is a okay. Now let's look at the parameter choices for UV systems. Okay, of course, V equal to O, that. Of course, V less than O, that, because you can easily guessing variables to make V equal to O since broken. And then one more interesting is, can I choose V as large as I want? No. So if V is much bigger than O, in particular, if V is bigger equal to O squared over 2, essentially, okay? There's a very nice attack developed by the research group of Tsuyoshi Takaki to show that this system actually can be solved very easily. How they do that? They essentially, okay, this is just a simplified description. With V big enough, you can do certain kind of change variables, essentially change the whole system back into some kind of triangular UV system, and can be solved easily. So this is their result. So which means V is less equal to O, bad. V is much bigger equal to O, also bad. So what do we do? So our suggestion is that we should choose V equal to 2 or 3 volt for practical applications. Okay, this is what we would like to choose for practical applications. And you will ask me, how about security? In addition to the Kibni-Shamir attack I described, you would ask me, hey, what are other possible attacks? Of course, the main attacks, we can categorize them into 3 categories. Number 1, direct attack. Number 2 is a reconciliation attack. Number 3 is a collision attack if you use salt. Okay, so let's look at those attacks. What is a reconciliation attack? So let me simplify the reconciliation attack. Okay, so in my opinion, the simple way to describe the reconciliation can be described to find the null space directly by solving a system of quadratic system. Yeah, because you can pretend you can find the basis for the T inverse O, okay? And then since the basic property is that it vanishes in the system, then you can just calculating corresponding equations. And then these are again quadratic systems, okay? And so in the end, the complexity becomes solving a system of all quadratic equations in m variables. So here V bigger than O is essentially back to the same system we will describe. Okay, and then you have this collision attack. Okay, So this happens if you use salt. This is something I mentioned later. But here, there's a huge memory cost. Okay? And this is direct attack. So what is direct attack? Direct attack is, so here we have a system of equations with more variables than equations. One thing you could do is just guess the variables such that the number of equations is equal to exactly the number of variables, and then solve. And if we do experiment, it's very clear the system behaves just like a random system. So this is not a problem. Okay? So this is a more or less a very quick summary and brief description of oil vinegar schemes, in particular unbalanced oil vinegar schemes. Okay, now I would like to talk to some of the things we are working on and during this preparing process. We submit something to NIST already in February, and then we got feedback asked about proof of security, especially about US CMA. Okay, and there was a paper written by Sakamoto, Shirai, and Hiwatari in 2011. This paper described some kind of proof of security for UV and HFE. Okay, so in order to achieve this so-called proof of security, a salt introduced. So what does salt do? So here, instead of hashing just the document, we'll hash the salt and add a hash the salt plus the document. Okay, and the salt is added, in my opinion, okay, is essentially for the security proof. Okay, so what does it do? So what really the salt help us do is that, suppose during the signing process we fix vinegar variable first. If we could not find a solution for the one hash, then instead of choosing another vinegar, we'll choose what? We'll change the salt and try again until we find a signature. Okay, let me repeat. The salt was introduced to ensure that any random guessing of vinegar variables, we can produce a signature. Okay, but if you do that, I mean, the system is less efficient in the following sense. So in our design, we actually fix the salt first, and then again change the vinegar variables if we select the values if the signature doesn't exist. Why do we do that? Because in this case, it's a little bit more efficient. Okay, and so therefore the proof of a SSH 11 cannot be directly applied to us. But if you look from practical attack perspective, we don't see any difference. Okay, so here one thing I would like to point out that after studying very carefully the paper of the SSH 11, their definition of a UV problem has some issues related to the distribution. So here maybe my time, okay, it's 40. So yes, maybe I can still say it. Yeah, it's 40 now, not 45 yet. Yeah. So the definition of the UV problem, we feel probably not in the standard form. The reason is related to the distribution, which means during the security proof, if you look at the image Y, you can assume Y to be uniformly randomly has a randomly uniform distribution in the image space, or instead you choose Y a contour distribution of the image of the Fn. I don't know if I make it clear. So there are very subtle differences in this consideration, and we feel the definition has some issues, we think. Okay, and so for us, we cannot achieve the same proof because we fix the salt and then change the vinegar. But from practical perspective, we don't feel there's any difference. Anyway, we'll write something up to give a proof of the UF CMA. Okay, this is the one thing different. Okay, Number two, the new things we do, this is also happened in Rainbow, is we're talking about the compression of a public key and private key. Okay, and a simple observation or simple description what happened is that we realized that during the generation process of the public key, we can choose a certain part randomly and the rest can be computed. And this technique was first proposed by Abraham Petot. Okay, and we can use that to reduce the public key size and the private key size. I'm using seeds and so on by like 60 or 70%. However, this comes at a cost. Okay, which means if you store your keys, public key or private key, in the compressed form, then you have to expand it to sign, and then you have to expand it in order to do the verification. Therefore, your efficiency will be reduced. So that's what we do differently next. Okay. Okay. So this is what we do new. So therefore, for the UV submission, we'll do we have this normal version, and then we have two different versions which are related to compression of the keys. So this is the compressed version. Okay. And these are the parameters we propose to choose. We have UVIP, UVIS, UV3, and UV5. So the first two are corresponding to level 1 security, and then the level 3 and the level 5. So here maybe I will talk about the level 1 case, right? Level 1 case, the first choice we'll choose Q to be 256, which means we choose the field size of 1 byte. And then here M equal to 44, which means there are 44 equations, N equal to 112, which means there's a 112 variables. Okay, so if you calculate the difference, which is 68, that's the number of the vinegar. Okay, and the second version is Q equal to 16, which means we're working on the field with half the size, half a byte size, and then here M equal to 64, and N equal to 160. Okay, and then you our public key size, and secret key size are given by tens of kilobytes. Okay, and the signatures are given by one is 128 bytes, another one is 96 bytes. Okay, so this is the basic description of level 1. Okay, and performance-wise, okay, you can see we have very fast signing and verification process. It's comparable and better, okay, than dilithium and so on. Okay, so that's the performance of these schemes. So therefore, they are very computationally efficient, and for both verification and signing process. Again, if you don't compress the key size, then of course, dilithium is much better. Okay, so this is the basic designs we intend to submit. Okay, and then the last part, I would talk about a new attack. This is a new attack we discovered. We call it a new mean rank attack. Okay, and the description of this attack is very simple. This is actually related to what we did for attack on the HFE V case. So let's look at one more time. The matrix corresponding to the essential maps. So here we consider the case of other characteristic. Okay, you have E equal to E1, E2, and E2 transpose. Okay, and if you look at the bottom rows of E2, bottom rows of this matrix, you realize all these vectors coming from the vinegar space. Okay, so if you pick given any row, okay, you pick them, okay, which means you will pick all of them, they are still in this subspace. So we cannot do much about it. But if you pick more rows, and if the number of rows times O is bigger than V, then you realize the span of the space still is a subspace of a dimension V. And that gives you a new way to describe a new attack using mean rank property. Let me repeat. So the attack is essentially find a nice row space basis such that the span of those space Okay, you have to collect a few of them. Once they are once O times the number bigger than V, then you can do a mean rank attack. And in this case, the rank is V. And we did some check. Actually, we worked with Max and so on, Daniel and so on, and we checked. Very unfortunately, or very fortunately, the complexity is very high. But nevertheless, this is a new direction to that deserve to look very carefully. So this is the new mean rank attack. Okay, and then again, I come back to the proof of security. Still, people ask me many times, can you do something proof secure? I think we have a chance. We have some new ideas. Hopefully, we can find enough time to submit to NIST. So we actually considered this following case, which is if we have a system of equations, the number of variables equal to the number of equations equal to n, the number of variables equal to alpha times n squared. The alpha is a number between bigger than 0, less than 1/2. We believe we can build some system such that we can reduce our security to this, sorry, not the PQ problem, MQ problem. Let me repeat that we believe, okay, we're doing work on it now. Hopefully we can catch the deadline. Is that we can develop a new system such that we can reduce our security to this MQ problem. Okay, and this new development is very much inspired by discussion I had with Daniel Smith-Tony when I visited him in Louisville a few months ago. Okay, and this is a combination of this method of solving highly underdefined system developed by Takagi and so on, and combined with vinegar. So we call it actually TUV. I think we have a chance to do that. So this is what we have now. Okay, I think my time is coming up, and so this is the end of my talk. And thank you very much.
Thank you very much, Jin-Tai. So let's wait for the question in the chat. So maybe we have a question here at NIST also.
I have a kind of I like to ask you to give some more explanation about by you add some salt randomized, then by manage this salt you can find a signature. Will that this may be a stupid question.
No. Yes.
Improve the efficiency of
No, it's that method does not improve the efficiency. No, instead it's cheaper to change the vinegar variables. The reason is very simple. And so if you fail the signature scheme, if you fail given a vinegar, if you fail, which means after you guess the value, the linear system you solve is how to say, is degenerating, which means not a full rank, which means if you describe the system as a span, one way to solve to see your solving linear system is you can view as you have a basis and then you have a span and then you want to find a vector expressed in terms of coefficients of the spans. But if the system is not full, which means you don't have a basis, you have n vectors, they are linearly dependent. So therefore, in order to be able to solve, you have to make sure your hash will fall into the subspace generated by those vectors.
Yeah.
So therefore, the probability is low. The probability is 1/q.
Okay. So by managing change the salt, you can make sure that the hash will go to that subspace.
You will go, but your success probability is lower than just changing the vinegar variable.
I see. But what is the advantage of using salt?
And the proof of security is the proof by SSH in 2011 requires that.
Okay, I see.
Yes, and then in some way we can claim that salt can help us to maybe to prevent the side channel attack and so on, and fault attack or something. But it's not very clear to me. We have to, I mean, we are now trying to write down clearly. Is it true or not? It's how much a help those salt in terms of channel. Yes. So the really, in my opinion, the beginning, the driven force for salt is more or less geared towards this 2011 paper. But we want more efficiency, therefore we did not really follow exactly. Therefore, their proof cannot be applied directly. Their proof cannot be used. Because over their case, they fix vinegar and then change salt. But in our design, we fix salt, then we change vinegar, then the proof cannot be applied.
I see. Okay.
Yeah. So, but from practical perspective, I don't see any difference. I have to be honest.
Okay.
Yeah. So this is something we are cleaning up. I hopefully in the next 1 or 2 days we can clean up completely.
Yeah, that's
yes.
a very short time for a big question, I guess.
yes. And we are looking very carefully after the paper of the SSU paper, and some of my colleagues really got into the details and find the definition. Their definition of UV problem has some problem. We think it's not in the standard form we expect, related to how the distribution is described. So hopefully we can clean up, but here I would actually like to ask you guys a question, how important it is. So suppose we slightly deviate, suppose there's some proof, but then we, in the final design scheme, we slightly deviate a little bit from the provable security version. I don't think it matters too much, right?
Yeah, that's a good question.
I will let you answer this one.
Yeah, well, that kind of balance is no linear relationship between the provable security and the efficiency, right?
No. Yeah. So, but on the other hand, it's easier.
No linear relationship between provable security and the real life security.
True.
These are complicated, and I hope at some point we can find an equation to map. But
okay.
There will not be a linear equation here.
No. Yes.
So we have 2 questions in the chat now. So yes. The first one is if I heard correctly, you propose 2 versions regarding the signing algorithm, the standard one and the modified version introduced in SSA.
Second, I don't understand the question. Just a second.
I think it's you basically already replied to this one. I think it's considering the versions you're gonna propose to NIST competition. You will have 2 different. So the question is, will you have 2 versions?
No. We have only 1 version. No, I think we'll make up our mind.
So you will not have a version where you do what the request in SSH paper, modifying the salt every time. That's what you said.
That will. I think from implementation perspective, it's less efficient. In particular, if you happen to have a signing failed, or you happen to have a degenerate linear system, then you're kind of in trouble. You know what I mean? Yes, it will affect much more.
Yeah.
Yes. We will not propose 2 versions. No, I think we'll just propose 1 version. That's it.
Yeah, and your signatures are still randomized. If you pick the salt at random every time and pick other vinegar variables, so I guess this is fine. And so the other question is, can you contrast to Rainbow and explain why your proposal is more secure and what the trade-offs are?
I wouldn't say it's more secure. So let me go back to the history. Like the reason at the beginning we did not submit to UV is because we were having a higher estimate on the min rank attack. So therefore, if you look at the performance, Rainbow is way better than UOV. Once the unbalanced oil vinegar attack, once the min rank attack become much more efficient, this advantage of Rainbow start to fade. I think Rainbow is still okay. Rainbow is, I think I can change numbers slightly, and then Rainbow can be just as secure as a UOV system. From my understanding is that I think Rainbow is fine. Still, probably from this perspective, you don't like it anymore, but that's fine. I think Rainbow is okay. But in general, when you design a crypto system, I think the simpler the better. So that's what I believe. And if you look at UOV system, it's really simple. It has gone through 20 years, more than 20 years attack. And if you really look at this attack, except the new min rank attack described, which is not efficient at all, I think we did not really make any new attacks for 20 years. Okay, and actually recently I spent a little bit of time. I realized actually there are fundamental mathematical problems we haven't looked carefully. So if you look at the Rainbow, if you look at the UOV, the UOV essentially, and let me repeat, is find a common null space. Okay, and I actually looking for reference given a quadratic, find is a maximum null space. I couldn't find a way to do it efficiently. So this is actually giving me more confidence. This is something actually extremely interesting. Essentially, the only way to do it is find solving a quadratic system of quadratic equation system. So therefore, I think the simplification is the simple design, and the easy and simple design is good. So I mentioned a little bit earlier that we start to see possibility to build some much more complicated system to achieve some kind of proof of security, but I don't know. That's more psychological. I think I think UOV looks as solid as anything. I mean, we could do. I mean, there's not much. How do I describe it? There's not much structure you can use except this single property, which is shared common null space of quadratic forms. Yeah. So that would be my answer.
So this is a nice transition to the next question, which is on a high level, what is special about UOV that has made it resist cryptanalysis for so many years when many other multivariate schemes have been broken?
I think a simple structure, that's it. And so I mentioned a little bit earlier, you can also view oil vinegar as a kind of in spirit of LWE. Okay, essentially the LWE add noise to the linear system on the coefficients on the constant part, and you can view LWE add noise through quadratic polynomials. And I think it's all coming from its simplicity, and there's no other structure except common shared null space of quadratic forms. Yeah, this is all I can think of now. And yeah, I have been thinking about attacking UOV for 20 years, and this is the only structure we could ever use. I mean, this new description of this new discovery of min rank attack, I think is interesting, but we cannot do much, I think. I mean, at max, I mean, you helped us to do some concrete calculations. It's interesting theoretically, but it seems not much we can do.
Yes, we do have a lot of hope for for this one, but it's still interesting, and yeah, I agree with you. The direct attack looks to be the limiting one in all cases.
Yes, and, yes. I mean, the reason I describe this accumulation May attack, it seems accumulation May is the only intelligent attack. This is in my opinion. All other attacks are essentially solving system equations. That's all. Back to the game, same game, which means you are solving system even more complicated than direct attack or other attacks.
And it's very interesting the comparison you made with LWE. Yeah, thank you for that. It's a new point of view on the problem, and that's quite interesting. And so I think we have time for one last question. It's kind of the second part on the one about the salt for the signature. Do you
Yes.
think that the distribution, of the signatures that produced in both methods are the same, or do you think they must be different?
What do you mean distribution of signatures the same? What do you mean by that?
The distribution of the signatures, if you use fixed salt and you pick new vinegar.
Yes. No. I think they are actually different. No, they are actually different. I think they are different.
And so I'm gonna add something on top of this question. So do you think that it could be easy to derive an attack from that, or you think that
No.
And...
No, you cannot. You just cannot. I don't think so. Because I mean, maybe you're talking about timing attack or something, but I don't think so. Yeah, from attack perspective, I don't see any way you can use the fact. Okay, so let me repeat, right? The fixed vinegar and then change salt is less efficient once your system is not, once the matrix corresponding linearity is not invertible, because essentially you are forcing your hashing into a subspace of a lower dimension. This is what you. If the matrix is invertible, you have a whole space, therefore given anyone you can find an image and solve it. So if the system is not invertible, then what? Then the span of the column vectors is a dimension of a space of a lower dimension, and in order to be able to sign, your hash has to fall into that subspace. But in the case of a fixed hash and then you sign, and you can see each time you just ignore it. You can throw away the case all the degenerate system. As long as the system is not invertible, you just try again. And then in this case, I mean, the failure probability is 1 over q. So therefore, in this case, it's much simpler to handle. And the distribution should be very different. And one more thing I would like to emphasize is that one way to look at the distribution is the space itself, which means you look at the FO, and you have a uniform distribution on it. But another distribution is very interesting. If you look at if you pick any vector from Fn, okay, from the original space, and then map to map to the image space from Fn to Fo, of Fo plus V to Fo. If you look at the distribution coming from randomly pick X and then map to Fo, and this is not uniform. And this is related to what the question asked. I don't think the distribution is the same. No. And if you want to prove a security, the fixing hash, fixing vinegar and then change hash is doable. The other one we cannot. At least we could not. We could not push the proof through because we cannot handle the distribution.
Perfect. So thank you very much, Jintai, for this talk. So let's thank the speaker again.
Okay, thank you very much. Okay, thanks.
So have a nice day, everybody, and see you for the next PQC seminar.
Okay,
Bye.
thanks. Okay, good night. Okay, bye-bye.
Bye.
Bye.